Welcome to my third tutorial in statistical thinking titled Visualizing and Summarizing Variation in Quantitative or Measurement Data. We will begin to understand the variation in measurements by visualizing the variation in summer temperatures around the world. Here we see the distribution of summer temperatures across two time periods presented in an article in the New York Times. The article goes into an in-depth discussion of what the shape of these curves mean with regards to climate change. For our purpose, there is simply a good illustration of what natural variation in measurements often look like. Take the figure on the left-hand side, summer temperatures from 1951 to 1980. Most temperatures are in and around the middle of the bell-shaped curve presented, the grey shaded area of the curve. As we move our eyes away from the middle of the curve to colder or warmer temperatures, a smaller proportion of summer temperatures are either very cold or very hot. Notice the tiny red shaded area of the curve at its rightmost tail, representing very hot summer temperatures. This means that only a very small percentage of countries experience very hot summer temperatures from 1951 to 1980. Contrast that curve of summer temperatures with the one on the right, showing summer temperatures from 2005 to 2015. We see a major shift in the curve to the right. As we can see, this means a much higher proportion of countries are experiencing very hot summers and a much smaller proportion are experiencing colder summers. Another example of a normal distribution of measurements is men's heights in the US. The data is presented here in what is known as a histogram. The histogram shows men's heights in centimeters from a random sample of 2,742 individual men. The sample data was collected for the 2011-2012 National Health and Nutrition Examination Survey, also known as NHANES. The distribution of heights has a symmetric bell shape, which peaks at the center of the graph. The interval with the highest percentage of individual heights goes from 172 centimeters to 176 centimeters, with approximately 22% of individuals having a height within that interval. Move away from the center bar, and the declining bars show that the percentage of individuals with height values greater than 176 centimeters or less than 172 centimeters decreases quite rapidly. The smooth, symmetric, black-lined curve drawn on top of the histogram is known as the normal distribution. This order to be found in nature and in random processes can be demonstrated with a simple coin toss experiment. Imagine tossing a coin 4 times and noting the number of heads you obtained. When you toss a fair coin 4 times, you expect to get 2 heads. But it is possible that you would get anywhere from 0 to 4 heads. As an experiment, imagine repeating that same process a very large number of times, tossing a coin 4 times and noting the number of heads you obtained each time. If you were to take all the data collected, the number of heads you got each time, and created a histogram with it, it should take on the shape of the normal distribution, as we can see in the figure here. The number of heads you expected, 2, is the average in the middle of this distribution. It is the outcome of the experiment that will happen most often. The distribution of data from purely random processes, like this coin toss experiment, will take on the shape of the normal distribution. This is a result we will take advantage of and reason with throughout the remainder of these tutorials. We have begun to understand variation through visualization of the data. We will now begin to summarize the variation in the data with sample statistics. To begin, we want a sample statistic that is a good measure of the center of the data, a typical value. The sample mean is considered a typical value for measurements that follow the normal distribution. Under the normal distribution, the mean is located where approximately 50% of measurements are less than this value and approximately 50% are greater than this value. The mean is a type of average, a measure of central tendency. The sample mean is a summary statistic that is an approximate estimate of the population mean. The sample mean is calculated by simply summing up all the measurement values in our data and dividing by the sample size. For NHANES men's heights data, the sum of all the height values is 477,277 centimeters, and the sample size is 2,742 men, resulting in a sample mean equal to 174 centimeters. As we can see from the figure presented, the sample mean of 174 is in the middle of the normal distribution of measurements. What this means is that approximately 50% of men's heights in the sample are below 174 centimeters, and approximately 50% are above. The sample mean is a useful measure for summarizing our data under the normal distribution, providing a typical value for our data. However, it tells us nothing about the spread or variability of individual height values around that sample mean. Why do we need a measure of the spread of individual measurements around the sample mean? Let's look at a hypothetical example to understand why. Let's say we were told that the sample mean weight loss on a diet program was 20 pounds, based on a sample of 15 individuals. Let's look at hypothetical examples from two weight loss programs that resulted in the same sample mean weight loss. The mean weight loss is 20 pounds for both weight loss programs. We can see that there is much greater variability in individual weight losses on the first program than on the second program. On the first program, one individual lost 55 pounds, where another individual gained 15 pounds, negative weight loss of minus 15 pounds. Individual weight losses on the second program are much more consistent, narrowly spread around the mean. The greater the variability in individual weight losses, the greater the uncertainty in how effective the weight loss program is. Therefore, we need a measure of the variability in measurement values. The statistic used to measure the spread of individual measurements around the sample mean is known as the sample standard deviation. The sample standard deviation measures how far, on average, we would expect an individual measurement value to be from the sample mean. For the NHANES men's heights data, the sample standard deviation was calculated to be 7.7 centimeters. What this means is that we were to select a man at random from the US population, we would expect their height to be approximately 7.7 centimeters from the mean of 174 centimeters. This does not mean that a randomly selected individual's height would be exactly 7.7 centimeters from the mean of 174 centimeters. It simply means that it is the distance or deviation from the mean we would expect the value to be on average. The greater the variability in individual measurements, the larger the value of the standard deviation will be. It is a measure of the variability in measurements around the mean. So far in this tutorial, we focused on measurements that follow the normal distribution. However, not all data is normal distributed. There are many examples of data that follow what are known as skewed distributions. This is where data has either a small percentage of high values, known as a positively skewed distribution, or a small percentage of low values, known as a negatively skewed distribution. When a distribution of measurements has a small percentage of high values, the mean gets pulled up towards those values, making it no longer a good measure of central tendency. When a distribution of measurements has a small percentage of low values, the mean gets pulled down towards those values, making it no longer a good measure of central tendency. In these cases, we use what is known as the median as our measure of central tendency instead of the mean. 50% of individual measurement values are always below the median, and 50% of measurement values are always above the median, no matter what the shape of the distribution of measurements looks like. The median is unaffected by the small percentage of low or high values in the data, whereas the mean is affected by those values. A good example of a positively skewed distribution is household income in the US. The histogram presented here shows the distribution of US household income in 2014. In 2014, we can see from the histogram that the median household income was estimated to be $53,700, what is also known as the 50th percentile. In other words, 50% of US households earned less than $53,700, and 50% earned more than that figure. Also, we see that only 5% of US households earn more than $206,600. The distribution of US household income is possibly skewed. The small percentage of very large household incomes pulls the mean up towards them, making the mean a poor measure of central tendency. A more interesting story emerges when we compare mean and median US household incomes over the 50 years from 1967 to 2017. The data is included in a report by the US Census Bureau in a table titled Households by Total Money Income, Race and Hispanic Origin of Householder, 1967 to 2017. The table provides the percent distribution of household incomes adjusted for inflation over that time period, including means and medians. According to the table, in 1967, the percent of US households with an income greater than $200,000 was 1.1%. This percentage has been slowly but steadily increasing over the decades, with 7.7% of households in 2017 earning more than that figure. In other words, a small but increasing number of US households are earning a greater percentage of total income. A related and even clearer indicator of this trend is the ever-widening gap between the median and mean household income. In 1967, the gap between the median and the mean was only $5,500, whereas by 2017, the gap had grown to around $25,000. There is a lot of debate in the US regarding income inequality and whether a sort of class divide has been emerging over the last number of decades. This data is certainly a good indicator that this is what has been happening in the US. No matter what the state of the economy over the last 50 years, more and more of the wealth has been moving steadily to a small but increasing percentage of US households. At the onset of the coronavirus pandemic, tests for the virus were in very short supply. However, a news article in the New York Times titled, "Need a Coronavirus Test? Being rich and famous may help," discusses the fact that the rich and famous were gaining access to tests without exhibiting symptoms, while people exhibiting symptoms and healthcare workers on the front lines were unable to get tested. The virus has exposed the reality of income inequality in the US like nothing else could. So far in this tutorial, we have learned to understand variation in measurements by visualizing individual measurements in a histogram and summarizing the variation with measures of central tendency, the mean and the median, and a measure of spread of individual measurements around the mean, the sample standard deviation. We have also discussed how the distribution of measurements often follow what is known as the normal distribution. The normal distribution is not simply a bell-shaped curve. It also has other characteristics related to its mean and standard deviation that we need to be aware of and understand. In the figures presented, we are looking at the distribution of men's heights data with the histograms removed so we can focus on the characteristics of the normal distribution. For data that follows the normal distribution, approximately 68% of individual values are within one standard deviation of the mean, and approximately 95% of individual values are within two standard deviations of the mean. This is known as the empirical rule for the normal distribution. For the men's heights data, this means that approximately 68% of individual heights are between 166.3 centimeters and 181.7 centimeters, the gray shaded area of the curve on the left-hand side. Approximately 95% of individual heights are within two standard deviations of the mean, or between 158.6 centimeters and 189.4 centimeters. This second characteristic of the normal distribution is one we will reason with throughout the remainder of these tutorials. In this tutorial, we learned how to reason with the normal distribution of individual measurements. In our next tutorial, we will learn how to reason with the normal distribution of sample statistics.